present what he did last time?
Sure, yeah.
Okay, go ahead.
Yeah, so I'll just give a reminder, I guess, what I was working on before the summer. So I was working with on that quantum dropout implementation. So yeah, we had a circuit, something like this, which we used to encode images. These are images from the Eurosat dataset, land use, land cover images. So we would encode these images with RZ rotations. These theta values here would just we'd replace those with the pixel values from the image, and then alternate these with square root of x gates to encode the image. And then we'd entangle the qubits with these C0 gates. The C0 gates we wouldn't apply on every pair of qubits, but just the qubits which are connected in the quantum computer we're using, which is the IBM Kolkata quantum computer in our case. And then we'd measure the qubits with respect to some observable. Again, we wouldn't measure all qubits, but just a subset of them so that we don't end up with a huge distribution at the end. But I've been measuring 8 qubits. I selected the 8 qubits that are connected to 3 other qubits in the quantum computer. The other ones have at most 1 or 2 connections, but there's 8 with 3, so those are the ones I measured. And then when you measure it with respect to some observable, you get a distribution like this one here. This is, of course, only for 4 qubits, but it would be much larger with 8. And then the idea with the quantum dropout was to use this distribution in place of the uniform distribution that's usually used to select which neurons to drop in that layer. But we were finding that this quantum circuit can't really distinguish between the different classes of the data set. And so that kind of meant that the dropout layer wasn't really data driven in a sense. So that was, yeah, as much as I did on that. And then more recently, I've been working on kind of using this same quantum circuit or a very similar one for just pre-processing the data and then training a neural network to classify based off those distributions instead of directly off the images. So it's kind of like a pre-processing step before we apply a neural net. And so I did that. I ran the images through here and computed the distributions with 8 qubits for a few different observables. And then I created just a really simple linear neural network for classification. So it was just a few linear layers using ReLU as activation, and then some dropout for regularization. And so this input layer is just a vector of size 256, right? Because it's that's 2 to the 8 because we're measuring 8 qubits. But I wasn't really able to get very good classification with this. And of course, I played around with the number of layers and the architecture of the network in general. But the best I was able to do is about just over 30% accuracy, right? Which is pretty bad. So I then thought maybe if we include several observables in the input data, rather than just a single observable, that might give the network a little more data to work with and produce better classification accuracy. So yeah, I created another net this time. Just so I took 3 of these distributions, for 3 different observables on the same image, and then just stacked them together to form an array size 3 by 256, and then applied a convolutional layer to that with a 3 by 3 convolution, and then a few linear layers. Again, just a really simple neural network, but wasn't really able to achieve anything better with that. At most about 35% accuracy. And I was using, there's a hyperparameter optimization framework called Optuna that I was using for optimizing hyperparameters. But again, yeah, even with that, couldn't really achieve any sort of decent classification accuracy. And of course, it's overfitting quite a lot too, even with the dropout layers. So I thought maybe I'll try one more time, just add a few more observables, see if that increases accuracy at all or not. And so I computed, 6 observables. So I think these were, the first 3 observables were X on all qubits, a Y on all qubits, and a Z on all qubits. And then the other 3 were like combinations of the X, Y, and Z Pali observables. And yeah, the same neural network architecture as last time, just a convolutional layer and some linear layers. But again, wasn't really able to achieve anything better than about 35% accuracy. So that's pretty much as far as I've gone on that so far. I don't actually have a slide for this. I should have, but I also just created a very simple network, kind of similar to this one, that just takes the images rather than the distributions. So without the quantum preprocessing step. I just wanted to see if the poor classification results were due to the simplicity of the network. But I was able to achieve, roughly like over 70% accuracy with just a very simple network like this. So yeah, that kind of tells me that it's not just the simplicity of the network that's producing that's not giving results. Yeah, so that's kind of as far as I got to on that.
I have a question.
Yeah.
There are no trainable weight in your quantum circuit, right?
No, not in the quantum circuit. It's just like a pre-processing step.
Yeah, okay. And did you run it on a real quantum computer, or was it simulation?
No, it's all simulation. Yeah.
Yeah, but I guess that even if you put parameters on the circuit, you will not be able to train them with the PyTorch. What is it? Is it a grapper that allows you to use Qiskit parameters and optimize them at the same time as PyTorch neural nets? But even in this case, you will not be able to train it because you're not using the expectation values to train the neural net. You're using the probability distributions, and you don't have a shift rule. To compute the gradients on circuits for probabilities, only for expectation values. Yeah.
All right.
Everybody got that? So basically, and the way that we compute gradients on a quantum circuit is with respect to an expectation value of an observable. And then we do something that we call parameter shift to find the gradient with respect to the parameters on the circuit, and then we do optimization with the gradient. But in order to put this, who's sending messages? Okay. Yeah, so for this case, what we're using is the probabilities, and this shift algorithm that computes the gradient for quantum circuits does not work with respect to probabilities, like only with respect to expectation values. Now, probably something can be done, but it's not clear to me that you will be able to train as you use this processing of the image and then fit it the probability distribution to the neural net. I'm not sure. I need to look into it more in depth.
So can we conclude that, by the way, Jan, yes, it is a classifier. Can we deduce that the probability distribution that we get from the encoding of the images are not different when you change the image or the class of the image? So you can't differentiate between the probability distribution of a crop and of a river, for example. I don't.
Okay.
Yeah, I think that's what we can conclude, because we are not able with this encoding of the data to tell a difference, so to help the classifying.
Yeah. Yeah, so you're saying maybe we could try a different observable per class.
Yeah, but how do you know that? Or during training, yeah, you could.
Yeah, during training.
Yeah, you could use different observables.
Yeah, one observable per class.
And 10
Because
classes.
your data is already labeled.
Mm-hmm.
Okay, do you see that, Adam?
Yeah.
So when you pre-process the data, instead of measuring the same observable for all the classes,
yeah,
do one class has its own observable, and then for the other class put another observable.
Okay.
And
But,
I don't know if the difference would be obvious even with different observables, but I think we could try.
Yeah, it makes sense to try it, I guess.
What would we do during testing of the neural net then? Just assign a random observable?
Oh no, no, you do the same thing. So your data comes labeled either if it's train or test. And what you do is for each label, for each class, you associate an observable, a different observable.
Okay, but I mean, in general, when we're testing a neural net, we don't know the class beforehand, right? Because that's what we're trying to.
I see the problem. Yeah, you're right.
Is it, just have a question, is it for 10 classes you're training?
Yeah, it's for 10 classes.
I would try first just a binary case, like one class against another, because
you mean with a neural net?
Yeah, it's a simpler problem and you can be scaled after to many classes.
Yeah, right. I don't think we could have a different observable for each class, because it doesn't make sense when you don't know anymore what class it is. You know, when you're trying to classify, what observable would you choose?
Can you, but you know how many classes there are? But if you have 10 classes, why don't you try for a new data sample, you try all the different observables you already know, and you do a forward patch for each on the same neural net, and then compare the probabilities to see which one is highest. So it will be like an ensemble of classifiers that come from different observables.
Yeah, okay. So you're training your classical network to work with the probability that is given by the observable of that class. And then afterwards you try all the observables and you take the could work maybe.
Yeah, it maybe it's too naive and I don't see a problem yet, but yeah, because the observable, if the image like look the same, so you make like the same kind of rotations on the circuit, and you put a specific observable, you should see something different than if you change those patterns and put a different observable. Which observables were you using, Adam?
So the first three were just X on all qubits, Y on all qubits, and then Z on all qubits. And then I just did kind of random combinations, XYZ, 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 or something like that.
Okay, I see. And did you choose it like really random? So for each qubit, you throw a uniform variable for 4 different polyarrays?
You mean like to determine the observable? No, I mean, I didn't like use any sort of random generator or anything. I just came up with them.
Oh, so, yeah, you just came up with something random. That's okay. Okay.
Yeah.
Yeah, because look, it is not clear how to choose the observables, but we can choose very different observables. So just make sure that the observables do not commute, for example, because if they commute, the expectation value will be the same. So that means we cannot differentiate between the classes.
So I think Samuel is right on that. We could start with just 2 classes. So we have 2 different observables, which are very different in that sense that they don't commute, and then work from there. I think 2 would be a good start.
Yeah, start with 2, then you add 3, and see how it goes.
Okay.
Yeah.
Sounds good.
I mean, if you want to keep on working on this, I don't know if it's someone else's turn.
Yeah, no, I'm happy to continue a little bit.
Okay.
You're getting 45% accuracy. You're getting 35, right?
Yes, 35.
I think it's better than random. That's a good news. I'm trying to be the cheerleader.
Correctly, Adam, you tried to generate different generate an encoding with which the probability distribution that you get at the end would differ according to the class. You tried that, right?
Yeah, so I tried quite a few different encodings like earlier in the summer when I was working on.
Oh yeah, and you had also some heat maps. Did we show the heat maps here? I don't remember.
Yeah, I did show them at the last meeting in July.
Okay.
I could probably find them again if you want to see them again.
No, that's okay. But yeah, I think that's the idea.
Yeah, I think maybe the same idea, but this time with the same encoding but different observables for first 2 classes, then maybe more would be great. I don't know if you have kept the framework of generating the heat maps and stuff, but could be nice to have them if it's not too much work. As Marco was saying, I could continue working on that, or somebody else if anybody is interested. Yes.
Yeah, no, I'm happy to continue, but yeah.
Yeah. Okay. Yeah. Cool. So look, for now it's as you can see, just trial and error. We try different ideas and see what happens, what we can improve, what else we can do, and so right now we tried a couple of things with Adam and nothing seems to work. So in case you would like to start reading more papers instead of trial and error for now, because like after this, I think we'll be running out of ideas. There seems to be a couple of new papers online, or if you have an idea of what you would like to read specifically, go ahead.
I think there was the Quantum Week last week. I don't know if you guys attended the conference. Because it would have been nice to have some kind of overview of the conference or what was the big papers.
But you attended the Quantum Week?
No, I think just John attended. I think John Pilarte, but I don't know if he wants to.
Okay. Yeah,
I
John,
was wondering.
you want to present something at this reading group, and you have like you can give like a summary of what happened that was interesting for QML at the Quantum Week. Go ahead, just let us know. And in the meantime, Adam can start working on this. I'm not sure if I should give you guys 1 week or 2. Yes, Mario.
Yes, I would like to know if you can have access to your work, Adam, somehow to see. Is it a Python code, a notebook? I would like to see that and maybe have access to your data encoded. Is it possible? Just
Yeah.
to,
yeah, I
to
can
play with it a little bit.
Yep. Yeah, I can upload it to the GitHub probably.
Yeah.
Informatique.
So those of you who again don't have access of for the GitHub, just you can write to either me or Marco, and we will give you access to the GitHub where Adam's code is actually.
Yeah.
Okay.
There should probably be on a branch called Adam or something like that, or Quantum Dropout. I don't remember.
Yeah, there is a quantum dropout branch now. I could put it on that one.
Yeah. Yeah. We can move to that branch for now. Sadola, do you have a question? Oh no, sorry, it was Mario again.
Oh, why not? I have a question again.
Okay.
Just as you mentioned, I think the features done by quantum, and the rest is classic.
Yes, it's deep learning.
Yeah, deep learning. So, so encoding, indeed, converting the picture to encoded the picture was done by quantum circuit. Yeah.
Yeah.
So, do you want to optimize the features here using the quantum
no
circuit or something?
No. We don't want to, and it's not clear how we could.
Okay.
Yeah.
So, so indeed, the main problem here is back to the features. I think featurization.
Yeah.
So, so I didn't get is that you want to use two classes for this to figure out how.
Oh, because you will need to evaluate different observables. So this will mean running different circuits. And right now we are simulating 27 qubits. So I guess at least in terms of resources, it makes sense. Because we need to wait, well, Adam needs to wait for the results to come back from the IBM simulator. Because 27 qubits is too much to run locally, I guess.
Okay.
Yeah.
Actually, I am running it locally. It seems to be a little faster. Yeah.
Oh, nice. Okay. Good. Do you have a big ass computer or something like that?
I mean, it's not huge. It's like a 16-core PC, but it seems to work all right.
Okay. Nice. Perfect.
Yeah.
Okay. Thank you.
Yes. Mario, another question?
No.
You're still okay.
No, okay.
Sorry.
Maybe I have a question. Would it be possible to have an approach similar to PCA, where or an autorecorder, where you try to reconstruct the input image? So you get quantum features, but the goal is just to be able to reconstruct the input image, so something similar to that, because that way you will optimize your representation in the quantum world. Then the resulting embeddings could be used for classification. Does it make sense what I'm saying?
Not in the quantum computer, but there's you cannot do PCA on the quantum computer, right?
But similar to like some kind of low-level representation of image, but that would be optimized in the quantum.
Yes. So you cannot do that, but
okay,
there is a quantum algorithm to compute the SVD. So, for instance, if you have too large a matrix and we want to compute its SVD, maybe we can do something else, but that will be like changing completely. Well, no, it will still be QML because it will be machine learning and it has something that is quantum. So I will classify it as QML.
Just a remark. I see that in Qiskit there's a quantum autoencoder examples. So I don't know if it can be useful. So you can create, as Samuel has said, an embedding that is more related to the information in the image or your observable from your observable.
Yeah, the quantum autoencoder is not related to an autoencoder as a neural net. So as a neural net, you can reduce the dimensionality, go to a subspace where the data it highlights on certain directions, and now you have your data embedded into a lower dimensional space. And now the decoder can decode any distribution like from that latent space. But on the quantum side, what you're trying to learn is quantum states, not features. So if you want to reduce dimensionality, it wouldn't work like in the same way. Like in the classical side, if you have a classical autoencoder with a neural net, you just need to go and take the neuron values from the latent space.
Yeah.
Right? But you cannot do this on quantum because it is a quantum state. You cannot just go and get the quantum state. You will get probabilities.
Yeah, for sure. Yeah.
Yeah.
Okay, I see.
Yeah, although I haven't really looked in detail to the autoencoder, and if you want to follow that direction, maybe we can look for a paper or two, and we read it and we go through it to understand what it does. It could be another direction.
Just because I see an example in the casket, I don't know what they are doing.
That's okay.
But
yeah.
But I said maybe it could be an interesting avenue to see. Because you're before feeding things to the neural network, maybe you can test if those embedding are correct or good. Have you tested like a projection like TSNL, looking if already they regroup themselves in classes in their in space. TSNL is an algorithm to reduce the number of dimension in 2D from n dimensional vector, but it can be useful that at first to see. You can have a good idea if it's gonna work. If you have only a big ball, it means that everything is the same, and I don't think the neural network after that can do much better. What is feeding is not better. I don't know.
Yeah, I was thinking maybe a brute force approach would be because you said there is a random aspect in your circuit for the first stage. Maybe it's to choose randomly different configurations that will give you different input for your neural network. And the question is there one better than the other, or is just equally bad? If you have random configurations that are better, it means you can probably search for a better solution in the quantum space. You see what I mean?
Yeah.
So it's very raw, it's very brute force, but at least you know there is a landscape out there. But it's very crude. You see what I mean? It's also a lot of computations.
Intense in resources.
Just another question about your curve about training and test. Is it possible that you do not have enough data to train with your when you're using your like over it looks like the validation overfitting because you just don't have enough data? Is it a possibility?
Yeah, that also could be it because you're using what 100 samples per class?
No, I'm using I'm using the full data set, and I'm using an 80-20 training testing split. So it amounts to, I think there's 27,000 total training images split into 10 classes.
There is no data augmentation in that somehow, because you have to first pre-process them.
Yeah, no.
So, yes, so somehow you're very far from what we're doing. And
yeah, I don't think it's possible to do. Yeah, that augmentation would be very, very demanding, I think, in that case.
Yeah.
That's a good point. If you want to counter overfitting, but you still get a minimum of loss in testing. There is a minimum in the generalization gap you're getting. So there is something there, but I think just the features are not good enough for the for the neural network. So. But the question I have, do we have better features? Like just looking randomly, if we could, I don't know how long it takes to train all of that, the full pipeline.
Yeah, the actual training of the neural net doesn't take long, but it takes about 3 days to compute the distributions
The
for
distribution. Okay.
the data.
3
for
days.
one level.
Okay. How many data samples?
So I think there's 30,000 in total.
30,000, 3 days. So you can.
So I think if you do a 2-class problem, you're gonna downsize your training set.
Yeah.
But then if you could add more random choices in terms of circuit configurations, that would, enable us to confirm or confirm that there is a better solution out there. But
Right.
interesting.
Yeah, I don't know if we should do more observables or different encodings.
Maybe both.
Both, but it's gonna
I'm not
be
sure.
costly. And you're better not testing the two at the same time, I guess, in order to know what does the difference. So maybe one run with kind of randomized encoding, and then see, as Samuel was saying, if there are some random encodings which are better than others, which means that the encoding does affect the training that we do later on. And then if that's the case, we could explore that avenue, or we could keep the same encoding but different observables every time and then see, are there any observables that give better results? But in this case, it would even be combinations of different observables.
Yeah.
Depending on the classes. Yeah. Lots of testing to do.
Yeah.
Actually, we could divide the tasks so that somebody tries the observables and somebody tries the different circuit embeddings.
Like if someone else wants to get their hands dirty. No, volunteers.
Yeah. I have to see for the code. I have to understand it. It works.
Yeah. Okay.
Maybe I can put some of my time over time.
Okay. Yeah. So maybe you can, you both can be in touch, like Mario and Adam. Like you can like update yourselves in terms of the code. And what do you think? Shall we meet next week, 2 weeks, so that you have something to present, like maybe the first experiments?
2 weeks.
2 weeks?
Probably 2 weeks. Yeah.
Yes. Perfect. And after that, I think I can start reading this paper on autoencoders. If there's more people interested, maybe we can try something else.
I could, if we need, I could present something on auto. I'm intrigued. I'm interested in that paper on autoencoders in quantum, just to for my own knowledge. I could explain the paper, or maybe this paper is from 2017, I believe.
Yeah, it's quite old, but I think it was one of the first papers on the subject. So we could try to find something more recent, or.
Well, I can check the literature, see if something came up last year or this year, and I could maybe not next week, but the week after, in 4 weeks maybe, but I could present something probably.
Yeah, perfect.
Okay, yeah, you can also force your student John to present what he saw at the Quantum Week.
Oh, John, poor John.
Yeah.
So that could be a good start for him, actually.
Yes. Okay, good. So that's the plan. We meet in 2 weeks. I'm saying goodbye because I don't see any other things left for us to do today, unless you have something else.
No, I think it's a good start because everybody's restarting. So I think we need a ramp up.
Okay, yeah, we can keep the meetings every 2 weeks.
Yeah.
We meet in 2 weeks, and Mario and Adam present what they found.
Yeah, Adam, you will have to send me your email.
Yeah, for sure.
You can put your emails in the chat.
Yeah.
That's the easiest, I guess.
The chat. Where is the chat? Okay.
Yeah, I think I only have access to the Q&A, but I can put it there.
Yeah, because it's not US.
Yeah, I can do that. So
I don't know if you see my.
Okay. Okay, so can you see Mario's email, Adam?
No, I cannot.
And the Q&A?
I just posted mine in the Q&A.
Yeah. Okay.
Okay, I see both.
Okay. Yeah, I see both.
Yeah.
I see.
Adam.Smith 4.
Yeah.
Category. Let's see. Okay.
There's 4 Adam Smiths.
Yeah.
I guess so.
At least 4.
At least.
Okay, good. So I'll see you both. I'll see you all in 2 weeks, and then after that, 2 weeks more. Samuel presents on autoencoders.
Yeah.
That's the plan for now. Cool.
Thank you, guys.
See you all.
Thank you.
Okay, bye-bye.
thank you.
Have a good evening.
Thank you. Bye.
Bye.
Bye.